Okay, welcome to Computer Networks. This is lecture 13. Just wanted to remind you that there's a homework due this week, but not next week. Did people get messages about the deadlines for the homework? It's due on Saturday, not Wednesday. But that's a hard deadline, Saturday at midnight, so please submit it before Saturday midnight. Okay, yeah, question?
Is there a penalty for Saturday?
No, there's no penalty.
But you can't turn it
No, we cannot. Because we want you to enjoy your spring break. All right. Let's spend a few minutes talking about homework 6, if there is anything you would like to discuss. So those of you who got started with it, can you tell us, what's the main challenge here? So some people started, right? Did you start?
Yeah.
Who started?
How to measure the transfer rate? How to measure the transfer rate between the client and the server?
Yeah. How do you measure the transfer rate between the client and the server? Okay. Do you have some ideas?
I just looked at the amount of bytes being written to the socket.
Yeah.
And had a clock going
Yeah.
in each write and divided it.
Okay, so yeah, you could just keep track of the number of bytes that are being written to the socket and have an independent clock that keeps track of time, and every so often you look at the number of bytes being transmitted and the time elapsed. That gives you the data rate. Right? So what are the potential problems with this approach? Again, there's not going to be a perfect solution to this. What are the potential problems? Did you have some ideas?
I mean, you have to make sure you're measuring time correctly.
Yeah.
Because a lot of the built-in C stuff is either low resolution, nothing more than seconds elapsed,
Right.
or tells you processor time. It's only measuring how much time your process has had on the CPU and not actual elapsed time.
Sure. So one of the concerns is, depending on what function you're using to keep track of time, there could be some inaccuracy there. So that's a valid concern. Any other concern? How do you know how many bytes you're sending across the network?
Are we supposed to just measure like bytes of actual data, or are we supposed to include like TCP overhead and things like that?
Yeah, so that's a question. Yeah, I want you to make that judgment yourself. If you want to measure the TCP overhead, that's going to be a little bit more complicated. So if you don't want to do that, just you can do the segments, only count the payload if you want. What are the other problems?
How accurate do you want it? Because I mean, mine works within half a kilobyte per second, but you want it.
So one of the concerns is potential inaccuracy in measuring just the number of bytes. And why does your program only work at the granularity of half a kilobyte?
That's because of how I measured it. Instead of adjusting the amount of bytes written to the socket dynamically, I instead wrote my buffer size to the socket, and then I would wait for it to, like if it went over what it was supposed to in 1 second, it would add that to the next second, and then wait. So there's always a little bit of overlap. Does that make sense?
Yeah.
So it's only accurate.
Right. So the buffer size that you use is going to determine the granularity to some extent. And I'll just explain it slightly differently. When you call send, so first of all, how do you send data on the socket? If we're talking about C, what's the call? Send. Now, what are the arguments that you need to provide to send?
The array of data to be written and the length.
And the length, right? Yeah. So if you want the measurement to be as accurate as possible, how many bytes should you be writing at a given time? If we're talking about as few as possible, right? But we don't want to do that. Why is that?
Not very efficient.
It might not be very efficient, especially if we're sending a segment out for each byte. So it seems like there's some kind of trade-off here. Do people understand that? So another issue is, depending on how your system is configured, send might complete, but the data hasn't gone out to the network, right? And what's the implication of that particular property in terms of the error you're going to incur in your measurement?
It's going to be perceived as a longer time to receive the data because it's sitting there waiting to be buffered.
Yeah, but if you're just looking at from the perspective of send call and when it returns, it might return immediately. Then are you going to overestimate the number of bytes you are sending in a given time or underestimate?
Overestimate.
You might overestimate. Does that make sense? You call send and the system buffers it, and your application thinks, okay, the send is complete, but the data hasn't gone out. Does that make sense? And of course, you're thinking about latency. So how about, what's the implication on latency for the data in terms of what you measure and what actually happens in that case? So for data rate, it seems like we might overestimate, right? How about latency? So we call send, and so how are we measuring latency, first of all? I guess we have to answer that question. So one way of measuring latency might be one machine sends a message to, let's say, node 2, and node 2 is supposed to reply to that message, let's say, right? And then we keep track of time. We note the time when we sent a message, and we note the time when we got the reply, and we subtract, and we know the latency. So let's say that's the general scheme that we're using to estimate latency. And because of this buffering that I just mentioned, are you likely to overestimate or underestimate the latency? Let's just think about the buffer on the sending side. So we call send, and let's say we know the time when the send returns, because that's when we know that. So are we recording the time exactly when the data is sent, or just before the data is sent, if there's buffering going on? Just before the data is, and let's say the data goes to the other node. Let's say there's no buffering on the other side, just to simplify the discussion, and the message comes back, right? And we note the time, T2. We compute latency by using the formula T2 minus T1. So did we overestimate the latency or underestimate the latency?
We overestimate.
Why did we overestimate?
Because you're also counting time that's spent in the buffer.
Right.
In addition to time endpoint.
Yeah, because we actually didn't send the message at T1, right? T1 is the time at which the send returned. So you just have to worry about things like this when you're trying to make measurements in a real system. And we did this discussion just with one buffer just at the sending side. Now, things are going to get complicated if there are buffers on the sending side, receiving side, on both the nodes. So I hope you understand the complexity here that could quickly overwhelm you. So making precise and accurate measurements is actually very challenging, even for something as simple as data rates. I don't expect you to worry about all of these aspects of sending and receiving packets through the buffers when you're estimating the sending rate, but you still have to do something at least crude. And for that, it's perfectly fine if you just use a timer, as someone suggested, and keep track of the number of bytes you're writing. And that'll give you the number of bytes you're sending at a given time. So what are the other challenges? So any questions about how you might calculate an instantaneous data rate? It's pretty simple, right? You send bytes, you're keeping track of time. Based on that, you can compute bytes per second. What are some of the other challenges? Or let's say, what are some of the other ways in which this measurement might be flawed? Think network dynamics. Remember, we spent a lot of time when we were talking about transfer protocols, um, talking about how transfer protocols should adjust the rate in response to what? Congestion, or maybe some other users are starting to use the network, or something has happened to the network, right? So now you made this measurement, so what's the problem? So this measurement might be invalid immediately after you make this measurement, right?
Some other large flows could have come on.
Yeah, right. But again, we don't have to worry about that too much in this assignment because we're using relatively small rates. We're actually fixing the rates, right? But let's say you're writing an application, networked application, that monitored the rate at which it's sending packets, and let's say it wanted to adjust the rate depending on the rate at which it's able to push the packets. Things get complicated there, right? Because you're trying to push as many packets as possible at the same time measuring the rate at which you're pushing the packets, and that measurement might be invalid immediately after you make that measurement. All right, so that's one challenge. So what are the other challenges in this assignment? What are we trying to explore? So let me ask you this. How did you implement concurrent HTTP? Did you use select or threads, or did you use fork? Fork. So what's the challenge if you use fork?
Making sure that each process is aware of
How many bytes you're supposed to send?
yeah.
So how are you going to make sure that, let's say, n independent processes are, let's say, how are you going to coordinate the rate at which these various processes are sending the data? Because this might be long-lived flows, right? Let's say you have a server that forks the process and let's say start serving a request. That's going to take a while. And now there's another request that comes in. What should this process do? How should it adjust its rate?
The earlier process now.
Yeah.
There's now another connection, or it has to reduce its rate.
Yeah, so it seems like you're writing a network program within a server even. Does that make sense? So you have all these processes, they might need to adjust the rate, not based on the connection between them and their clients, but based on the number of aggregate connections that's coming to the parent process. And how are you going to get them to communicate with each other? What's the mechanism?
Shared memory.
If you use shared memory, that's fine. That's probably one of the easiest. You could do other mechanisms. What are they?
Use pipe. So whenever one process terminates, it writes a little pipe, and then I select that pipe. I select between the socket that listens and that pipe.
Yeah. So if a process terminates,
Yeah.
so the parent is going to know that this process has terminated, right?
Yeah.
Why does the parent need to know that the process has terminated?
Can you repeat?
So using this mechanism, when a forked process or a child process terminates, you're saying the parent will know
Yes.
that this. But why does the parent need to know the child has terminated?
So that it can adjust the rate for all the processes up.
Sure.
Yeah.
Yeah, but now let's say there is a new process that comes up and, in a sense, a request. How are you going to get all the processes that are already sending the request to downgrade their rate, reduce their rate?
Yes, I have a problem.
Yeah, but you understand the problem there, right? So it's not just termination. Whenever there's a new request that comes in, you have to reduce the rate of the existing processes. Right? Let's say you're sending at 10 megabits per second. When a new request comes in, the old process has to halve the rate at which it's sending the packets. The new process, it's easy, right? When you launch the new process, you can tell it, okay, send it at 5. But you need to somehow tell the old process that reduce the rate to 5 now. Just think about that, okay? What else did you find challenging, not obvious? In terms of testing, we will not do we'll use very simple tests. It'll be along the line that is on the description.
I guess if you're using multiple clients with multiple rates, it's going to change the rate your server sends for every single client that comes in.
Yes. We probably won't test it that way. Because the goal is for you to really think about, okay, what are the issues that you encounter when you try to measure the rate at which you're serving or you're using the network, and how to adjust it. So we probably won't test against those scenarios. We'll keep it simple.
Just to clarify, it's only the second and third parts that are supposed to be able to handle concurrent downloads?
Yes. So we server negotiate rate. Let's just fix that right now. Did you think about how you might do the first part? Client and server negotiate rate. This is single-threaded server, single-threaded client. Actually, we didn't do multi-threaded clients anyway. I want you to use something called, basically, you're supposed to use HTTP, not some special protocol between the client and the server. What that means is we're going to test your client and server for the first part with a standard client and a server. And it should still work. What that means is it should still be HTTP. The way the servers and the clients work, when they encounter a header field that they don't recognize, is typically just ignore it. Okay. So the client is going to add a special header field. The description already tells you what it is. And if you send this request to, let's say, a standard web server, let's say Apache, what does Apache do? It'll just ignore it, doesn't know what it is. Same the other way. Let's say we wanted server to send some special message to our special client, which we don't do it here. If we have a web browser, the browser might just ignore it because it doesn't understand that special message. But if you have a special client that's written to understand the special message, it can interpret that message and do whatever it's supposed to do in response to that message. So the key is the protocol still has to be HTTP. Any other questions? So just looking ahead, we'll try to release the next set of assignments pretty soon. We have a rough idea of what it's going to be. It's going to be routing. You'll learn how to do some routing. First, we'll do some static routing and forwarding, and then we'll do dynamic routing. We'll give you a shell code and some utility code so that you spend most of your time on routing and forwarding. And that's why it's taking a little bit of time.
Are those going to be up for spring break?
I'm debating. So are you planning to do homework during spring break? That's the idea?
Yeah.
Yeah. We'll put it up, as early as soon as it's done, so that you can schedule your time. That's the idea. Okay. But those will still be 1 week assignments. 1 week it'll be static routing and forwarding, and the second week it'll be dynamic routing. All right. Any other questions before we proceed? Oh, by the way, one other thing that I forgot to mention is I will send out a list of student presentation topics, maybe tomorrow or something like that, and we expect to have these 5-minute presentations in the class. Okay, so today we're going to talk about routing, just a very brief overview of the overview that we did last time, and really jump into these 2 routing algorithms called distance vector routing and link state routing. As we said last time, the internet consists of nodes of various kinds and various technologies that connect them. wired, wireless, right? This is what the global map looks like. It almost looks like there are all these lines connecting various parts of the world. It seems like if we were to come up with an abstract representation of the internet, it seems like we'll have some lines or edges. And it seems like there are some vertices there as well, right? So a lot of time when we're discussing the routing and when we're talking about some abstract scenarios, we might use a graph where a node might be a location, depending on the type of routing that we're doing. But most of the time, a node might be a host, internet host. An edge might be these technologies that connect the nodes, for example, wires or wireless transceivers, for example. We discussed the difference between routing and forwarding last time. Hopefully you don't make that mistake now. Routing is the process of understanding the topology and selecting the paths on which you should send packets. Routing is not about sending the packets, sending the data packets. So the router builds these tables called forwarding table that tells you, okay, if you have this destination, this is the link along which you should transmit the packet. In this piece of software called forwarding, actually it's a combination of software and hardware, it's called forwarder, will look up that forwarding table for hints as to what's the link, what's the interface on which you should transmit a packet for a given destination. And it'll do queuing, scheduling, etc. and for the packet. So for routing, the challenges are due to dynamics. The links go up and down for maintenance, for example, or bringing up new links, or phasing out certain links. It's a decentralized system, which makes it more challenging because there is no central server or location or authority you can go to and ask, what's the route between this node and this other node? Can't do that. It's decentralized. And finally, scale. We need routing system that scales to large number of nodes. Because in the internet, we have billions of nodes now. Because each cell phone is a node in the internet, right? Okay. So let's do a quick exercise here as an introduction to routing. So why don't you tell everyone your name?
I'm Josh.
Okay, we have Josh here. Why don't you tell everyone your name?
Zach.
Okay, we have Zach there. So let's say Josh needs to send a message to Zach. And he's allowed to send message only to his neighbors. How would we come up with this system that will deliver a message from Josh to Zach? Okay, what are you going to do?
I'm going to look around for neighbors to send.
Yes, but which neighbor are you going to select?
I only have one neighbor right now.
Okay.
So I guess I'm sending it to my one neighbor.
Yeah, okay. And then what would you do?
Some neighbor, I have any option.
Why her?
This is closer.
Closer to you. But is that a good strategy always? Why might that be a bad idea sometimes?
You'll go through lots and lots of neighbors before you get to where you're going if the person's far away.
Okay, that's one. So one problem that was pointed out was you might need to pass the message many, many times. What's the other problem?
It might never get there if there's a long link somewhere that it has to go through.
Yeah.
And somebody says, oh, well, I've got this shorter link, I'll send it through that. And it'll never go through the one link it has to go with the bottleneck that it needs to pass.
Exactly. So let's say the two of you had the shortest distance between each other. Then you might just forward the message back and forth if you use that strategy, right? So you say, okay, she's the closest to me, send it to her. And she says, okay, she's the closest to me, and send it back to her. So we have a we have a loop. We'll never be able to resolve that. So can you come up with a different strategy? Because the goal is you've received a message, now it's your responsibility is to pick the next hop so that the message will eventually get to Zach. What will you do?
I would say how many edge between me and him, I should the shortest way.
Yeah,
I mean, the way we know his class.
yeah,
At least I mean people for hours.
yes. But you need to pick someone.
Yeah.
Who are you going to pick among your neighbors and why? Because your goal is to get the message over there. If you don't know the name, you can just point at the person. Why?
I think if I choose, they come back the message to the person next to him.
Yeah.
Go over there. Then I pass the card. They said to him, I go to the TA, but I'm like the TA to that guy is still wrong.
It's longer, okay. So let me put another constraint here. So it seems like you're trying to get a global view of the network. And that's not feasible in the internet. Why is that? There's too many nodes. You can't make these decisions based on your understanding of where all these billions of nodes are. You're typically making these decisions based on information in your surrounding, right? So do people appreciate the routing problem? So that's essentially the routing problem. Now, just to make the problem harder, let's say you're not allowed to see or hear. How would you make that decision?
Just randomly pick one.
That's
You have no information. You can't see or hear. Then all you can do is randomly pick something.
exactly. So that's actually one of the routing algorithms. It's called a random walk. It's probably going to take a while to get to the destination. But even when you're doing a random walk, what you could do is keep track of the fact that you've already seen the message or not. And if you receive the same message again, maybe you could tell the person who was trying to forward the message to you, I've already seen this message. Maybe you should try a different neighbor. You could maintain that kind of state.
Seems like it would be a lot of overhead to remember every message that you've seen.
It might be. It might be a lot of overhead. And that's the reason why we don't use it.
Yeah, it might be easier to put that information in the packet list of all the nodes it's passed through.
Yes. So one concern was it might be a lot of overhead to remember all the packets that you've seen in the past. A solution that was proposed to address this problem, which is put the information in the packet itself. Now, let's say you're passing the message across a large number of nodes, then how big is this packet going to get?
It's going to grow.
Yes. So depending on the network, you might maybe use one strategy or another. Let me give you a slightly different algorithm, which will simplify this particular message routing problem that we have in this classroom. So let's say we want to use something called geographic routing. And this is how the algorithm works. Every time you receive a message, you know the destination for that message. And you're going to select the neighbor that is closest to the destination. The assumption is you know the geographical coordinate of each neighbor that you have, which is essentially what you're doing to some extent. Because you said you want to send a message to him, and that's maybe because he's closest to the destination, among your neighbors, of course. That's not how we route packets in the internet, but that's an example of a routing algorithm. And you could build a protocol, and it becomes a routing protocol. It's called geographic routing. And the particular algorithm that I described is called greedy geographic routing. Why is it greedy?
So you always want to get to the destination as fast as you can.
Yes. That's why you're picking the neighbor that is closest to the destination. So every time we have a greedy algorithm, we need to be worried about something. What is that?
maybe it goes into the longer way or into the.
If you find a solution and if you have a very greedy algorithm, you're going to find a pretty good solution actually. So the optimality of the solution is usually not the concern. What's a concern with greedy algorithms?
It'll only ever use that one best link and then eventually saturate.
Yeah, so you might only use that one best link. Another concern usually when we have algorithms like that is it might not work in all the topologies. Can you think of a topology in which it might not work?
I actually have that issue.
So let's
that,
say, go ahead.
That here in Houston, because if not all of the different ISPs that are active here in Houston have connections here in Houston, and so I've done trace routes on stuff that I've sent to other nodes in Houston, and I'll watch it hop out to Dallas and then to Atlanta and then back on somebody else's ISP back into Houston.
Yeah.
And so if I'm always trying to get to the closest geographically, I'll stay forever in Houston where there isn't a connection to get to the network I need.
Okay, yeah. So if you're just using greedy geographic routing and if you're trying to send a packet from one node in Houston to another, it might not work because there are a lot of nodes in Houston that are not connected to each other and require external connections for them to be connected, right? But let's just think about the topology here. Let's say you have the packet, and what would you do? Who would you send it to? The destination is over here.
How many hops can you get to Zach? How many hops for you to get to Zach? How many hops for you to get to Zach? Take the message.
Now the problem is, let's say you actually don't have a neighbor on this side. So what will you do? Because let's say he's their only neighbor.
The message is already been through there.
Yes. Because among your neighbors, he's the closest to the destination. Right? Does that make sense?
Yeah.
And what is he going to do? He said, among my neighbors, he's the closest.
Yeah.
So that's a greedy algorithm, right? Okay, good. So we hopefully we got an intuitive feel for what routing algorithms do. So routing is the process of selecting the next hop in a topology, and we talked about various types of routing protocols, but we're not going to worry about them too much. We're going to actually now discuss the routing protocols that are used to forward real packets. Okay. So before we get to the description of those two routing protocols today, let's put them in context to understand where they are used, because there are various types of routing protocols used in different parts of the internet. So here's a map of the internet, a very abstract one. So we have a bunch of backbone service providers. These are big ISPs, AT&T, Comcast, etc. We have smaller ISPs. These are called consumer ISPs. Again, we're going to talk about them in detail later. And we have small corporations and large corporations hanging off of these ISPs. For example, University of Houston, we're probably a large corporation if we wanted to map ourselves to the slide. And we have some ISPs. That's how we get internet connectivity. And when we need to send a packet to a different corporation, we send our packet to this ISP, and then this ISP will forward the packet to that corporation, right? So this is the overall map of the internet. These ovals, those are called autonomous systems. You can think of them as organizations for now, or ISPs or something like that. And each autonomous system has a bunch of computers, right? A bunch of hosts. For example, let's say that large corporation is University of Houston. It's not just one computer, is it? How many computers do we have?
Lots.
Lots, yeah. So it seems like there are two sets of routing protocols we might need. One, to route packets within these corporations or within these networks or autonomous systems. And another set of routing protocol to just route packets between these autonomous systems. We call them interdomain and intra-domain routing. Interdomain routing would be the protocol that tells us how to route packets between various autonomous systems. And intra-domain protocols tell us how to route packets within a domain or an autonomous system or an organization. The scaling properties that we desire are different from these two types of routing protocols. Do we need to scale the routing protocol that we might run here, let's say, in this organization to millions of nodes? Probably not, right? But the routing protocol that we use in the larger internet, it definitely has to scale to much larger numbers than the one that we might use in a small organization, for example. Another big difference is within an organization, most of the time what we're looking for is probably the fastest way to get packets from host 1 to host 2, right? But when we're talking about the wider internet, that's not the only consideration. Money comes into play, hence policy-based routing. Why does money come into play when we're talking about the wider internet?
It costs money to keep all those connections going.
Yeah, it costs money to keep all those connections, but there is even I think there is a different reason.
If you have multiple connections, you may pay more for bandwidth on one of them than on another.
Yes, but there is even a better way to describe that. Yes, you might have multiple connections and you might pay more for, but fundamentally, but why are you paying?
Because somebody else is controlling it.
Or you're trying to use somebody else's infrastructure. That's the fundamental reason why money comes into play, right? Once money comes into play, then we can start thinking about, okay, we might pay more, less, etc. But the most important thing is, you need to pay someone if you're going to use their infrastructure. So in interdomain routing, it's dominated by policy. When it's time to decide how you should forward the packets and where. So when we talk about routing protocols and when we're trying to understand how the protocols work, as I indicated earlier, we use this abstract view of the network. So what are those circles? Nodes, routers, right? And what are those edges?
The connections between them.
The connections between them. What's the difference between a node and a router?
That can be a computer, it can be or a router.
These days, there's no difference between a computer and a router. If you think about it, they all have processors, they all have memory, they all have network interfaces. Right? So what does a router do? What's the if you had to distill its functionality to just one most important functionality of a router, what is it?
Forwards the packet to the next router.
It does not. What's the difference between routing and forwarding?
Routing decides where it's going to go.
Yeah.
Forwarding actually does it.
Yeah. So router decides where the packet should go, right? But so in order for it to, so we're saying the router makes a decision where it should go. What does that tell you about the number of interfaces it might have? So typically my laptop has one or two interfaces, right? Say that again?
It has multiple interfaces.
Yeah, it usually has a large number of interfaces. If you just had one interface, would the decision making be simple? Well, why would it be simple?
You can only use that interface.
Yeah, exactly. So you only have one interface to use. So recall, we said router decides. We should use this interface. If you want to get here, you should use this interface. That suggests that the router has a large number of interfaces. Not necessarily very large, but it's going to have multiple interfaces typically. So that's the main difference that you might want to keep in mind when we're thinking about hosts versus routers. And these edges have numbers. What are they? Yeah. So if you just want to talk graph theory, you might just call them edge weights, right? To make these discussions simpler, we represent various properties of links as numbers. For example, latency. What is latency?
The amount of time required to traverse that link.
Yeah, so latency is the time it'll take to traverse that link. And we might just assign the weight to be the latency of that link, right? What kind of latency is desirable, low or high?
Low.
Low latency, okay. How about bandwidth? How do you, do you desire high bandwidth or low bandwidth?
High bandwidth.
You usually, high bandwidth probably, okay. Can we represent bandwidth as a number? As long as we agree on the units, we can, right? Okay. And we can use other types of weights or cost. So the routing problem is finding the lowest cost path between the nodes. That's the routing problem. There is one aspect of cost that is worth remembering. Some metrics, these are also called metrics, some metrics are additive. For example, we want to find the lowest cost path between C and F using the latency metric. We can simplify the sentence saying we want to find the path with the smallest latency between these two nodes. If we know the latency for each link, can we estimate the latency for the whole path? Yeah. How do we do that? Just add them up, that's right. Okay. How about bandwidth? Let's say these numbers represent bandwidth. What bandwidth will the path CF be able to support? The minimum of all, the bandwidth of each link on the path. So you realize that not all the metrics or cost functions are going to be additive. Right? Okay. Another type of cost function could be reliability of the link. Some links are more reliable than others, right? Do you think that metric is additive or non-additive, or how would you compose those metrics into something called path metric? It's a reliability. And a reasonable way to represent reliability might be by using probability, right? So let's say, we use probability to describe how reliable a link is. Probability of, let's say, the number 1 means perfectly reliable, you don't drop any packets. 0 means you drop all the packets. So how might we use them?
Be multiplicative. You multiply the probabilities so that it will make it through each link.
Yeah. So we might multiply that particular cost function to compute the cost for the entire path. So depending on the metric, sometimes we might take min, sometimes we might take max, sometimes we might just add them up, sometimes we might multiply them to find the cost for the path. Another aspect of these metrics is thinking about how we find them in the first place. So let's go back to latency. And let's focus on node B. So how will B know that the latency of the link BE is 1, and BA is 3, and BC is 4? How? Is there a central entity that sends a message to node B and says, okay, here are your neighbors, and here are the latencies? Do you think that's how it works? Or maybe there's a different way to do that?
B probably just knows that it has 3 neighbors and it does test communications with each of them, just determine the statistics of the link.
Yeah, so maybe B discovers that there are 3 neighbors, and using a series of measurements and experiments, it might determine that, okay, these are the latencies. So each node is independently going to discover the neighbors and also the metrics for the links. Does that make sense? Okay, so let's just take a quick break, and then we can talk about these 2 algorithms. Now we've set the stage. In the meantime, if there's anything you want to discuss, you can do that. About homework, class, exam.
On the homework, is it only part 2 where you have to support multiple connections? Okay.
We'll pretty much follow the write-up.
Okay.
Of course, we'll use different numbers
Yeah.
for the rates and URL and things like that. But yeah.
So what would we have to do to program the fastest HTTP server possible? Like what?
Oh, was
what
that
would we have to
you?
include?
Was that you who posted the message yesterday? I think.
Yeah.
Okay. Yeah. I think you already learned that you don't want to use fork, right?
Right.
Yeah. There's going to be a lot of context switch. I think traditionally, people have taught that you want to use select, not even threads, to write the fastest possible HTTP server, and which you already, I think, discovered and found out, right? But there's been recent development about this, and the recent thinking is you don't necessarily need to do event-based programming to do the fastest. So maybe that could be, okay, so let's put that as one of the student presentation topics, and I'll provide pointers, and then we can have more in-depth discussions. But yeah, what's the problem with event-driven programming? Have you done even, is that what you did?
I mean, I wrote it using the equal,
Okay.
but
Did you select?
no. Well, I read that I had an implementation of select from a long time ago.
Yeah.
And I read though that for a higher number of file descriptors that you want to monitor, equal is going to be a lot better. It's going to be a lot faster.
But just generally, I was just asking, what's the challenge with using select as opposed to fork?
I mean,
You have to keep track of them.
Is it harder to program using select than to use fork? And why is that?
In my case, I see that the code is unreadable.
With select? Do other people share that experience using select? Or it's harder to read and follow at least with select than with fork? Do other people agree?
just barely. I mean,
Yeah.
there's only maybe 10 lines of code extra.
Yeah.
It's not like I did anything really special.
But let's say when you're debugging it and you have to kind of understand, okay, this is what happens, and then this is the next thing, this is the next thing. If you're using select, it's kind of hard to.
It's harder to visualize what's going on.
So that's called stack ripping. Basically, you're ripping the functionality to many places as opposed to, okay, step 1, step 2, step 3, step 4. That's why people have been doing a lot of work in coming up with a system that gives you the performance of asynchronous type programming, but without using select.
I mean, what could you use that would be faster than equal with multiple threads?
I'll send you a paper, and maybe would you be willing to present this maybe next class?
Next class.
Yeah. On Wednesday? It's just a 5-minute presentation. You already have a lot of experience, and it might be nice to share that with the rest of the students.
All right.
Are you planning to be here next class?
Yeah.
Okay. So let me send you the paper. And it'll be a good discussion. And that's one of the things I would like to do. Someone suggested that, and I had that in mind. But anyway, we should have discussions about various solutions to some of these homework problems. I think there's something important to learn there. We learn not only by just knowing one way to implement things, but also just finding out how other people implemented the solutions and what were the challenges. So we should definitely do that. All right, let's get started. So we're going to talk about two algorithms. We're going to spend much of the time with distance vector routing protocols, and then also link state. But once we understand one set of algorithms, it'll be pretty easy to understand the other. Before we get there, let's start with this abstract representation of a network. We have a network with 6 nodes, A, B, C, D, E, F, and you can see the links between the nodes, and the numbers indicate the cost, right? So what's the goal of the routing protocol? To build a table, right? That's the goal. That tells you for a given destination, here's the next hop. That's the goal of routing protocol. You do all the message exchange and computation to build a table. And who uses that table? Forwarding engine or forwarder, right? So each node is going to build its own table. So let's just think about what should be the output of this algorithm, and then we can discuss how we might design an algorithm to compute that output. So let's focus on E's table. How many entries does E have in its table?
Should have 5.
It should, but right now it only has 2, right? So this is just to make the slide cleaner. Just have 2 just as an example. What should be the cost for C? 12?
9.
Is it 12 or 9? So let's say we ran a routing protocol algorithm that computes the best route to each destination. So what should be the cost? So this is we're looking at E's table. So if E had to send a packet to C, that's what we're talking about, right? First row. So what's the cost? What's the cost of the best path from E to C?
9.
Why is it 9? Someone mentioned 9.
Go through F and then to D and then to C.
Yeah. And we're assuming an additive metric, right? Okay. So it should be 9 because if we go to F and to D and to C, even though it looks like a longer path, it's actually shorter according to that cost metric. It's 9. Compared to sending a packet directly, which would cost us 12. Okay, so it should be 9. Let's type 9 here. How about down here? So what are the possible paths from E to D?
E to C to D and E to F to D,
E to C to D and E to F to D.
and then E to C to A to D.
Exactly. There are actually a lot of possibilities, right? So which possibility offers the best path in terms of this cost metric?
EFD.
EFD. And what's the cost of that path, EFD?
3.
3. It's 1 plus 2. Okay, 3. Let's look at B's table. What's the cost of the best path? From B to A. That's what we're talking about, first row.
4.
What are the other paths?
Going through D.
Yeah, but that we don't want that. Why is that? Because that's longer. It's 8 plus 1, 9, right? So that's direct. How about B to D? It's 1. Direct path seems to be the shortest as well. Okay. So a routing table will not only have the cost, but also the next hop. Right? So let's say this was next hop instead of cost. What would this be? We're not going to have 9 because the nodes are A, B, C, D, E, and F. So what should be the next hop? Yeah. How about down here? So this is the output of routing algorithm. It builds this table that tells you the next hop for the packet, if you want to send that packet to the given destination. So let's say E needs to send a packet to C. You look at the table, and the table says send it to F. And F is going to have its own table that'll tell the node, okay, if you need to send a packet to C, you send it to D. Okay, so that's the output. So it's a local routing algorithm. That means you use information from your neighborhood. And the slide is a little bit dense, but it'll make sense. Each node maintains a set of triples: destination, cost, and next. So we talked about this just now, right? So for a destination that you need to be able to route to, you're going to maintain the cost, total cost of the path, and the next hop. We talked about that just now. And you exchange that information with the neighbors. Just with their neighbors, not the entire network, but just with the neighbors. A lot of times you do this periodically. Let's say every 30 seconds or every 10 seconds. Why don't you want to exchange this every 100 milliseconds?
It's too long. You risk your cost data being out of date.
100 milliseconds, it will not be long.
If you're doing that all the time, that's going to be a lot of extra traffic.
Yeah, and if you don't want to do it every few days because of the reason that you mentioned, which is the cost, and also the routing data might be out of date, right? So how are you going to? So if you had to implement this kind of algorithm, what update interval are you going to use? You need to pick a number at the time of implementing. When we're discussing in the class, we can just say, okay, don't pick too low, don't pick too high, right? What number are you going to pick? Okay, something for you to think about. Each update is a list of pairs, destination and cost. All right? So each node, so when you implement it, you're going to pick a number, hopefully. And whenever that timer fires, let's assume you're using a timer to keep track of the time at which you should send these updates. You're going to send these updates. It's going to be a list of pairs, destination and cost. This cost is the cost of the best path from that particular node. And if we learn about a better route than what we already know, we're going to update our table. Okay? Let's go back here. So which table? So can you tell me, is it information that looks similar to the one on the top right or the one on the bottom left that you transmit when you update your neighbors?
Bottom left.
The bottom left, right? Because we send the destination and the cost to our neighbors. Okay. So it's a little bit abstract, but if you relate back to the example, it becomes more clear. All right. So here is how we might update the path or the table if we discover something that's better. Do we want to update our route if we discover something that's worse? We don't want to do that, right? Why is that?
Because you don't want to take the worst path.
Yeah, because what is the objective that our routing protocol is trying to minimize in this particular version of the problem? the cost, right? Okay. So you know that you know the cost, the current cost, right? And then you receive an update from your neighbor, okay? So let's say your current cost is 10, and you receive an update from the neighbor 10, to a particular destination, let's say A, right? And you receive an update from the neighbor says, my cost to A is 5. Is that better or worse? So my current cost is 10, and I hear an advertisement from my neighbor saying that neighbor has a path of cost 5 to the destination. Is that better or worse? My current cost is 10. I suddenly hear about a path of cost 5. Did I hear of a better path or a worse path?
It depends on how much it costs to get to the person with the better path.
Exactly. We also need to consider the cost of link from the node to that neighbor that made that advertisement, right? Because the destination might be very close from that neighbor, but what is the distance to that neighbor? You need to consider that as well before deciding that you have a better path, and that's what we're talking about here. So your cost is going to be the minimum of, so during an update interval, you're going to hear a lot of updates. Each neighbor is going to advertise their best cost, right? So how are you going to decide which neighbor you are going to select at the end of the update interval? So what you will do is compute the path cost by taking into account the link cost to the destination through each of the neighbor from which you heard the advertisement. And pick the neighbor that gives you the minimum total cost. It's a shortest path algorithm, right? You probably studied the shortest path algorithm in some class. What is the class called?
Data structures and algorithms.
Data structures and algorithm. Did everyone take that class? Who did not take that class? Okay, good. Then I can go to the next slide. All right. Let's look at this as an example, and let's go through this exercise about what the nodes are advertising and what decisions they're making. Let's start with node A. I would also note that to make the discussion simpler, we're going to just assume the destination is A. All right? We're going to assume the destination that every node is interested in is A, just to make the discussion simpler. Otherwise, we'll have to send various costs for various destinations, right? So we're interested in finding the best path to A. So what is A going to advertise? So the convention is going to be ID, and then cost, and then path, okay? So what is A going to tell its neighbors? Its cost to the destination.
So I can get to the destination in 0.
Okay, so it's going to say 0, right? That's the cost. And what's the path? Path is A. Okay, great. You don't need to tell the path to other nodes. You just need, it's adequate for you to advertise just the cost, right? Okay. So which nodes are going to receive this advertisement? B, B, C, and D. Okay, good. And what is the advertisement? What is actually being sent? What information is being sent? What did A transmit?
A is 0.
It transmitted A is 0. And because we said everyone knows the destination is A, it's adequate to actually just transmit 0, right? Okay. So now B is going to receive that message. And B is going to update its table. how is it going to update that table?
Let's say cost A is 4, send A.
So B is going to say the cost is 4 and path is A because that's the next stop, right? Great. Is everyone with me so far? Yeah, okay, good. We're going to make things a little bit complicated here. And A also transmitted that message to C and D. Let's say those messages got dropped. Okay, so we're going to make things complicated here. The next round, B sent an advertisement. What did B advertise?
I can get to A in 4 hops.
Okay, so B advertised I can get to A in 4 hops, and A probably ignored that, right? So what is D going to do?
It's going to say it can get to A in 5 hops.
Or just cost 5.
Yeah.
Cost 5, and what's the path?
B, A.
The path, we can just call it B just to keep the screen clean. Okay, great. Everyone with me so far? Okay. And next time A sent its advertisement, the message did not get dropped. It actually got to D successfully. But before it got a chance to update that message, D also advertised its path to C. So how is C going to update its table?
Let's say cost is 11, next stop is D.
Okay. So what is the packet that was transmitted by D? What does it contain? As the
Just
cost.
The cost 5.
5, right? And then C is going to say, okay, from D the distance is 5, and the distance to D is 6, so it's going to be 11, and path is B. And remember I said B actually received the message from A in the next round. So what is B going to do? B received a message from A, and what does that message contain? What's the number that the message has?
4.
The message coming from A,
Oh, 0.
0. So what should B do? Or what should D do? Sorry, I confused you by saying B, but yeah. So D received this message from A, and that message has the cost of 0 because the distance from A to A is 0.
D ignores it.
So D should ignore this message from A?
Yeah.
Why?
The total cost is greater than its current cost.
Okay. So D will ignore it because even though the destination is 0 cost away from the neighbor, the total cost is going to be 8 plus 0, right? Which is larger than 5. Okay? But how about C? C also received that message from A. The message says, 0, right? So what should C do?
It's going to update
It's going to update to what?
2 and A.
2 and A. So this is how distance vector routing protocols work. Any questions? Because I think it's best to just discuss it using an example like that. So we talked about distance vector routing protocol abstractly, and now this is much more concrete.
If you get more complicated, like just say the internet in general, and you want to, each node, is it going to remember every single place that it's ever going to go to? Like Google and Yahoo and UH and whatever else.
Yeah.
Because there's, billions of possible destinations that it would remember to.
Right. Okay. So let's think about the multiple destination version of this algorithm, and then we'll address the issue that you just mentioned. So the advertisements are relatively simple here. You just send one number, right? That's because we're just assuming all the nodes are interested in knowing the distance to A, right? So if there are multiple destinations to which you need to find the routes, you have to advertise the cost to each of those destinations, right? And the concern here was, if there are millions of destinations, then are you going to have a huge packet? And if you use this algorithm, yes, that's the only way. Right? Fortunately, we don't use algorithm like this in the internet routing. We use these algorithms as algorithms for smaller network, for example, in intra-domain routing, and also in routing in wireless networks, multiple hop wireless networks, for example. But this algorithm is not going to work if there are. It could still work for millions of nodes, but it will not work for. We need to be precise there. Will it work with can you make this algorithm work with millions of nodes?
What kind of bandwidth? Really beefy servers or routers?
Any other approach? I would argue, yes, you can get it to work, given, let's not even think about bandwidth. Think destinations, right? If there is just one destination, it might be feasible to get it to work even in very large networks, right? But
Like if you're trying to get to the router
or
that
the
goes
gateway,
outside to the network.
right? But it might be tough scaling this to very large number of destinations. Why is that?
Because every destination you add, you have to add however many
Right.
nodes paths.
So you have to advertise the cost to each destination. Does that make sense? So just be precise there when we say, okay, it'll scale to large networks or not. Under certain conditions, you might be able to scale it to large networks. All right? Okay, let's see. Okay, this is what a routing table might look like. You have cost, you have next hop. Each node is going to have its own routing table, right? And when you're advertising, which columns should you put in the packet? You don't need to put all 3 columns in the packet. What should be advertised? Destination and cost, columns 1 and 2. Okay. Okay. So let's think about failures in the last few minutes we have. Let's say this link fails. Should the routing protocol know about this failed link? Yes, because potentially there is a path that goes through that link, right? So how should a routing protocol respond to this? Remember, our routing protocol does not take into account this link is up, this link is down. It captures all of that information using just one number, cost, right? So what should we do?
Have central value for link being down.
Yeah, so we can say infinity or a very large number, right?